Hello guys, welcome back to another video of Strength of Materials tutorial. But in this video, we will learn how to compute for the deformation of a statically indeterminate members. Members that are subject to axial load. But before that, let's try to understand first what is an indeterminate structure and how would you distinguish indeterminate structure from determinate. We have two types of structures. We have the first one, we have statically determinate, the most common one, in which our equilibrium equation such as the summation of forces vertical, summation of forces horizontal, and summation of moment are sufficient to calculate unknown forces. As we all know that the number of forces or the number of unknowns must equal to the number of equation. But if the number of unknowns exceed the number of available equation, then that could be considered as statically indeterminate structure. In statically indeterminate structure, we do not have enough equations to compute unknown forces. So equations like equilibrium equations cannot be used directly in determining forces. So we have to look for another equations that could be combined with equilibrium equations. And that we have what we call compatibility equation. Compatibility equation, this equation is derived using the deformation formula. So upon looking at the deformation diagram of our member, then we could create an equations pertaining to the behavior or the deformation behavior of that member itself. So that's how you differentiate determinate from indeterminate structure. So let's try to compute problem. I have here first problem. This is an indeterminate structure. We have the rigid platform has negligible mass and rests on two aluminum bars having 250 millimeter long each. And then we have the center bar that is steel and is 249.9 millimeter long. Find the stress in the steel bar after the center load is applied. And each aluminum bar has an area of 1,200 square millimeter and the modulus of elasticity is 70 gigapascal. And the steel bar here has an area of 2,400 square millimeter having a modulus of elasticity of 200 gigapascal. So we have aluminum here. Our aluminum is 250 millimeter long and our steel bar here that is 249 millimeter long. So therefore, there is a gap between our platform and our steel bar, and the gap is 250 minus 249.9, that is 0.1. So we have a gap here, 0.1. Now, since in this question we are asked to look for the stresses in the steel, so therefore, we need to compute for the axial forces in each member. Okay, so if we try to draw the free body diagram, we have 400 kilonewton that is acting downward, and we have three forces that is acting upward. We have the aluminum, the axial force, then we have the reaction from the steel and reaction from the aluminum bar. So therefore, we have three unknowns here, three forces. But by using equilibrium equation, that is summation of force vertical is equal to 0, and all the forces acting upward, that is we could have here PA plus PS, and then we have PA, and that is equal to 400 kilonewton. Now take note, since we have the same material of aluminum and they are in symmetrical, then we could say that aluminum here have the same axial force. So therefore, we have 2Pa plus steel is equal to 400. Now, this would be our first equation. But we need to come up with another equation so that we could compute for the unknown forces. Take note, since we have two unknown forces here, so therefore, we should come up with two equations as well. Okay, the number of unknowns should be equal to the number of equations. Now in this case, we cannot use summation of forces horizontal since we do not have force acting horizontally. We also don't have summation of moment since we do not have a moment arm or length distances here. So the only thing that we could have here is deformation equation, or we could create a compatibility equations. So how are we going to create a compatibility equation in this type of problem? Now take note, if we have 400 kilonewton acting downward, then there is of course a deformation in our aluminum. Okay? Now our aluminum here would go at this point. So our platform would be at this point after the load is 400 kilonewton of load is applied. So take note, this is only an exaggeration, no, just to internalize the deformation diagram. So this one here, this is the deformation of the aluminum. Okay? When our platform go to this line here, therefore we could also have a deformation in the steel bar. So therefore, we have here the deformation of the steel bar. Let's say that is our delta S. So at this point, to this point here, that is the deformation of our steel member. So by looking at the diagram, we could create an equation that is, we know when we have the deformation of aluminum member, that is equal to, we have the gap of 0.1 plus the deformation of the steel. So we could create this one, the relationship of the deformation of aluminum with the deformation of the steel, by looking at this figure here. Since our deformation of aluminum is just the combination of the gap 0.1 and the deformation of the steel. So this is now our compatibility equation. But we should simplify it further, and we should create an equation that is in terms of axial force in aluminum and axial force in the steel. So how are we going to convert this into this equation? Now take note, our deformation of aluminum here, that is equal to, that is from the Hooke's law, that is the deformation is equal to PL over AE. So we could say that our deformation of aluminum is equal to the force in the aluminum times the length of the aluminum over the area of the aluminum times the modulus of elasticity of the aluminum, is equal to, take note, this is our deformation of the aluminum, is equal to 0.1, correct? So we have 0.1 here, plus the deformation of the steel member, that is the axial force of in the steel times the length of the steel member over the area of the steel member times the modulus of elasticity of the steel member. So we substitute all the given values to this equation. We have, let's say that's PA, then the length of the aluminum here, that is equal to 250, and the cross-sectional area of the aluminum, that is 1,200, and the modulus of elasticity, that is aluminum, that is 70, so we multiply times 10 raised to the 3, and equals to 0.1 plus the steel, the actual force of the steel, times the length of the steel, that is, we have 249.9 millimeter over the cross-sectional area of the steel, that is 2,400, times the modulus of elasticity of steel, that is 200, then we'll multiply times 10 raised to the 3 so that we could come up with Newton per square millimeter. Now we can simplify it further, that is, we have 250 divided by 1,200 times 70 times 10 raised to the 3, we have, here we have 2.976 times 10 raised to negative 6, we have PA is equal to, that is, we have 0.1 plus 5.206 times 10 raised to negative 7, that is the actual load of steel. So we can transfer steel to the left side of the equation. Okay, that is we have 2.976 times 10 raised to negative 6 aluminum minus 5.206 times 10 raised to negative 7, that is the steel, and that is equal to 0.1. So this is now our second equation. So we have two equations now. So we could now use elimination method or substitution method to compute for the forces. Now take note, this is our first equation, correct? However, our 400 here is in terms of kilonewton, but this second equation here is in terms of Newton. So therefore, we have to convert this into Newton by multiplying 400 by 1000. So we have here 400 times 1000, that is 400,000. So we can now use this equation. So we have equation number 1, and this one here is equation number 2. So we use calculator, but you can apply algebra here to compute for the forces. So you can use by elimination method, you can also use by substitution method, and so on. But you can try to use it, or you can try to solve using your calculator. You can use your calculator to compute the unknown forces directly. You can use, you can click the mode button here, then go to number 5, that's the equation. Then you have, since you have two unknowns, you have xy here, so you click 1. Yan. Then you input all the coefficients. Now, if we set PA here as A, so you have the coefficient of PA, that is 2. Okay? Yan. Then the coefficient of PS, let's say PS is Y, that is 1. And the C here, that is the constant at the right side of the equal sign, that is 400,000. Then the second equation we have here, that is the coefficient of PA, that is 2.976 times 10, that is raised to negative 6. Then you have negative 5.206 times 10 raised to negative 7. And then you see here, it's the right side of the equal side, that is 0.1. Then click the equal button. Then you have here the value of PA, that is the X, that is 76,730.061, and you have the value of PS, that is 246,539.879 Newton. So these are the value of P and PS. So you have the axial force here. By using your calculator, we have PA, that is the axial load at aluminum, the 76,730.067 Newton, and the axial load on steel, that is 246,539.879 Newton. Since in this problem we are asked to compute for the stress in the steel bar, then we have the formula for the steel bar, that is the axial load on the steel member over the area of the steel member, that is equal to the axial force, that is 246,539.879, that is in Newton, over the area of the steel member, that is 2,400 square millimeter. So we have the stress of the steel member, that is 102.725, that is the Newton over square millimeter, or that is in megapascal. So take note, since we have compression, okay, since our member here are being compressed by the load 400 kilonewton, so therefore this is a compressive stress. So this is the stress of the steel. If you are asked to compute for the stress in the aluminum, then you compute for the stress using the axial load, that is 76,730.067. Now we have second example. We have a homogeneous bar with a cross-sectional area of 500 square millimeter is attached to rigid support. It carries the axial load 25 kilonewton, that is in P1, and we have 50 kilonewton, that is in P2, and determine the stress in segment BC. So we have to determine the stress of the segment BC. So the first thing we do here is, of course, to compute for the internal forces in every member, in every segment. In order to compute for the internal forces, we can use axial diagram or the cut section, but I think the most easiest one for me is by using axial diagram. So let's assume first that our external force at point D, that our reaction at point D here is in compression, or that is going to the left or acting to the left. Let's assume that one. Let's say that's our PD. And the reaction at A, that is going also to the left. So we have PA here. So these are all assumptions. So if we come up with a negative sign, therefore, so our assumption is incorrect. Okay? So since we are assuming that our PD here is compression, therefore we assume that our PD is downward. Okay? So therefore, in axial diagram, our PD, so let's plot PD here, that is below the axial diagram, that is negative PD. So all the internal forces between C to D are equal to PD. So that's the internal forces between C to D. Then after that, since it's our PD, take note we have tension, that is 50 kilonewton, that is going to the right, acting to the right, therefore we go up. Okay, so we have here, let's say this is our point here, that is negative PD plus 50. So all the internal force that is in between B to C are negative PD plus 50. So we stay PD here as unknown or as variable, since we do not have yet a value for that. Okay, then after this one, we have negative PD plus 50. We have 25 kilonewton, that is also acting to the right. So therefore, that is positive. So our diagram here will go upward. That is negative PD plus 50 plus 25. Then our internal force in between A to B is in the equation of negative PD plus 75. Okay, so therefore our PE here is PD plus 75. Since our first system is in equilibrium, therefore our diagram should end with 0. So therefore, these are the equations of internal forces in every member. So this is from member A to B, negative PD plus 75. This is negative PD plus 50 for the member BC, and that is only negative PD for member CD. So how are we going to use these internal forces? Take note, these forces, okay, each force in our internal members can produce deformation, okay? Could have created deformation in every segment in our bar. Okay? So therefore, we could say that our AB here has a deformation. Let's say that is our deformation of segment AB. And we also have deformation of segment BC. And we also have deformation of CD. So in this case, we will try to look for a compatibility equation. Now, since we know that our end A and end B here are rigids, so there will be no movement of A or D to any directions, correct? Since we have fixed ends. Now, if we try to create a compatibility equations here, we know that our D here will not move closer or farther from A. So therefore, our D here, the movement of our D here is 0. And how are you going to compute for the movement of D? That is just the combination of the deformation of every member. Correct? So our compatibility equation here, that is equal to just the summation of all the deformation should be equal to 0. Okay? So in this case, again, since we do not have movement in D relative to A, closer or farther from A or relative to A. So we have here the summation, or that is the deformation of AB plus the deformation of BC plus the deformation of CD is equal to 0. So in this case, we can now use the deformation formula, that is PL over AE. So we have here the deformation of AB plus the deformation of BC plus the deformation of CD is equal to 0. Now the deformation of AB here, that is the internal force in the segment AB times the length of segment AB over the area of AB times the modulus of elasticity of AB plus the axial force of BC times the length of BC over the area of BC plus EAB, and the axial force of CD times the length of CD over the area of CD times the modulus of elasticity of CD, and this must be equal to 0. Now the segment or the force in AB is equal to negative PD plus 75, correct? So our PAB here is equal to negative PD plus 75. So we have here negative PD plus 75. LAB, the length of AB, that is 0.6 meter, so we can say that it is 600 millimeter, okay, over the cross-sectional area of AB is equal to 500 square millimeter times, since we do not have value of E, so we let our modulus of elasticity here as unknown, but since this is a homogeneous bar, therefore our E here, or modulus of elasticity, is uniform all throughout. Okay, so we have the same material all throughout. So upon further simplifying this equation, we could actually cancel out E here, since our E is equal. So later we'll do that. Plus PBC, our actual for BC here, that is equal to negative PD plus 50. Okay, that is negative PD plus 50 times, we have the length of BC, that is 1.2, so therefore we have 1,200 here, over the cross-sectional area, that is since the same area all throughout, so we have 500 times the E, plus PCD here, our PCD is equal to the internal force between segment CD is equal to negative PD. So plus negative PD times the length of CD section, that is 0.9 meter, that is 900, over 500 square millimeter, that's the area, times E, and equals to 0. Now take note, they have common denominator, so by further simplifying it, so we could cancel out 500 times E, and since we have a 0 in the right side of the equations, correct? So this can be cancelled out. So we have here our equation that is equal to negative PD plus 75 times 600 plus negative PD plus 50 times 1,200 plus negative PD times 900 is equal to 0. Or we could have, we multiply, that is negative 600 PD plus 45,000. Then we have 1,200 times P, that is negative 1,200 PD plus 50 times 1,200, that is 60,000, minus 900 PD is equal to 0. So we can solve the value of PD here by further simplifying it. We have 38.889. Now, what is the unit? Since we know we are using 75, or we are using the forces here as kilonewton, and we did not convert it into Newton, so our unit here is in kilonewton. Okay? Again, since we are using 75 kilonewton, 50 kilonewton in this form. So directly, our answer will be in terms of kilonewton. But if you want to convert it into Newton, let's say you are using here 75,000, you are using here 50,000, then your result would be in terms of Newton, and that should be 38,889 Newton. Okay? So this is the reaction at D. Okay? Since we come up with a positive sign, so therefore our assumption that PD is acting to the left is correct. So we have PD that is acting to the left. Now after this one, since this problem asked for the stress in BC, so we have to compute the internal force in BC, that is PBC here, that is the actual force or the internal force in BC, that is equal to negative PD plus 50, or this gives us negative 38.889 plus 50 kilonewton, and this gives us 11.111 kilonewton. So using PBC here, our stress in BC is equal to, that is the actual force in member BC over the area in BC, that is equal to, PBC is 1.111, that multiply it by 1000, so that we could have Newton as our unit, over the area, that is 500 square millimeter. So we have the stress in BC, member BC, that is equal to 22.222, that is in megapascal. So this is now the stress in member BC. Our stress BC here is tensile stress, since our actual load 11.11 kilonewton is located above in our actual diagram, and it has positive value, so therefore that is tensile stress. And that ends our discussion in actually loaded indeterminate members. For more videos, please don't forget to like and subscribe.